Okay, kiddos. Here is an example of calculating the work done in lifting an object. So remember, we have the situation of some books sitting on a table. No work is being done. If, in order for work to be done, the books would have to be lifted through some distance. So the force that the table exerts on the books is in this direction. Remember, we could call that the normal force. And if the books were moved any amount of distance in that direction, then work would be done. So yes, if you were to sit there and hold books steady, it would feel like you were getting exhausted and your muscles were getting tired, and that is what's going on. But in terms of physics, you're not doing any work because an inanimate object with no energy required could sit there and do that forever. So here's an example. We have a person, and let's say they are carrying a 5 kilogram weight up this ladder, and they're going to carry it up and up and up and up and up and up and stand there. So I don't know, maybe this is the circus and they're going to do flips and jumps and a trapeze. That would be kind of exciting. So trapeze, and they're going to make it more difficult by carrying this weight. And the trapeze is 8 meters above the ground. So the person is lifting. When the person holds onto the weight, the force they exert is in this direction, because the force that Earth exerts is in the downward direction. Maybe off to the side we could make a free body diagram. So here we have our 5 kilogram thing, weight, and this is the force that the person exerts, and this is the force that the Earth exerts. Notice how they are balanced, they're canceling each other out. And so you wonder, well, what force does Earth exert on the mass? That, again, we call weight. So that would be mass times the acceleration due to gravity, 5 times 9.8, or 49 newtons. So in order for the person to hold that mass in their hand, they have to exert a force of 49 newtons in the upward direction. So when the person climbs, here they are partway up, and they're still holding this mass, they have exerted a force in the upward direction, and they have moved in the upward direction. And notice how they're kind of moving to the side. If we could draw a little triangle here, and it would be like this. And because the force they exert is in the exactly upward direction, all we're interested in is how far they moved upward, not how far they moved to the side. So if you were figuring distance, it would actually be this distance, not this, not this. So by the time the person gets up to the top, they have traveled a vertical distance of 8 meters. So when we go to find how much work they did on the object, how much energy they expended in moving the object to the top of the platform, we would multiply force, which is the 49 newtons, by the upward distance, and that is 8 meters. So let's see, 50, that would be 400, so this looks like a 392, and that would be joules. 840, I think. Okay, so hopefully that's right. And this is the total work done on the object in moving it from here to here. If we were to calculate the potential energy of the object, take a look at this. Potential energy is mgh. So we have mass times the acceleration due to gravity times the height. And look at this. This is exactly what we just did. We got 5 times 9.8, and then we multiplied it by 8. 5 times 9.8, and then multiplied it by 8. So all the work done on the object in moving it up goes into creating its potential energy. The work done on the object in moving it up, in lifting the object, is equal to the potential energy gained. So its potential energy down here was 0, its potential energy up here is 392 newtons, and it gained that potential energy by the work done on it by the person. All right.